Welcome to the next talk on GPU computing. Now, the first two lectures I gave an overview of GPU computing, and I laid the fundamental concepts, some fundamental concepts of GPU parallelism, and a few example algorithms. This is a coding day. This time I will actually tell you how to actually write code for CUDA C. And hopefully by the end of today you'll be able to walk out of here, write your own programs. That's my goal. So first I'm going to review what I talked about before just to refresh everyone's memory. After all, these talks are only once a week. And then I'm going to go through a few CUDA C examples, and I'm going to intersperse sort of generally comments about how to write code along the way. So let's review. So there's this thing called a single instruction multiple data paradigm. CUDA C programming is for this paradigm. It's in situations where you apply the same command to multiple places in a data set. And the idea is you can compute all those, you can run all those instances of that command at the same time. Compare this for loop where you add two vectors component-wise, where each component is, each set of components is summed up in sequence, with the CUDA C version, which spawns a million simultaneous threads, and then each thread gets this sum, and all threads compute these sums simultaneously. That's the sort of problem we're after, and this is where we can apply our GPU computing. We can parallelize a lot more than just loops. Now, when you start to go to code, you're going to have to keep this relationship between the CPU and the GPU in mind. You're going to constantly be sending instructions to the GPU and then reading back results. Just remember that the CPU and GPU relationship is kind of like a human pocket calculator relationship. The human does the thinking, most of the overall structure of the program, does the higher level management, and then only at certain stumbling blocks, when things would be really slow and really hairy, does the CPU send stuff to the GPU. And that's sort of how you want to make use of your GPU. Only send parallel calculations there, and then write your results back when you're completely done. Keep in mind that also this thin line between the CPU and the GPU here tells us that there is very low bandwidth between the CPU and the GPU, so writes to the GPU and from the GPU are going to take a long time. We want to be mindful of that. But parallel calculations, once we're on the GPU, are going to be a lot faster because there are a lot more cores. And as this thicker line between memory and cores indicates on the GPU side, there's some really high memory bandwidth between the on-chip memory and the cores. So once we get there, we can run parallel calculations a lot faster than on the CPU. And there's this thing called a kernel. I'm going to use the word kernel in the context of code this time, but a kernel is in general just some instruction set that you send to the GPU. And the GPU executes this kernel over and over again in separate instances called threads, all in parallel. And these threads are grouped into bunches called blocks. And why do we do that? Well, threads inside the same block can communicate and share memory far more easily than threads in different blocks. And sometimes we want threads to be able to synchronize. And I'll talk about synchronization a bit later. But it's important to have blocks for those reasons. And the sum total of all threads in a kernel is called a grid, for probably graphical reasons. I don't know. Historical reasons. So if the CPU tells the GPU, for example, to sum pairs of adjacent numbers in this array, the GPU thinks that sum pairs of adjacent numbers is the kernel, and the data is this vector. And what it might do is it might spawn two blocks, each with two threads, and it might divide up it might allocate this task to the threads, its minions, like this. We might have two blocks in this table, each with two threads, index 0 and 1. And each thread gets a pair of adjacent numbers to sum up. And that's how we might think of doing things in parallel. And last time I went over a lot more examples like this of algorithms in parallel, and I told you what you can divide up into blocks, what each thread in those blocks do, and that sort of gives you a general idea of how you want to structure your calculations and partition them into threads and blocks, and where you might want to synchronize those threads within blocks. So that's what I covered last time. And just remember, we can also have threads and blocks in 2 dimensions. I'm going to stick with 1 dimension for now. This diagram also reminds you that kernels are executed sequentially. One is completed before the other begins in your code, unless you're doing parallel streams, and that's a whole CPU computing thing, and that's more complicated. I'm not going to get into streaming and the concept of GPU computing. Just I'm going to make the oversimplification that kernels happen sequentially. Most of the time they will. In each kernel, we'd have a partition of blocks. Each block is partitioned into threads. Notice these words at the top, host and device. I'm going to use host a lot to describe the CPU and device to describe the GPU. I don't know why the CPU is called the host and the GPU is called the device. That's just kind of the lingo. You'll see that a lot in the documentation. And I'm going to start using it because it'll make the coding make more sense. Now, originally it didn't always make sense to think about GPU computing in the sciences and in statistics, because the only languages originally you had to program on the GPU were graphics languages, and they were clumsy for scientific problems. It wasn't the way you would think about science. It's the way you would think about programming a video game. But there's this thing called CUDA, called Compute Unified Device Architecture, that lets us use a language not entirely unlike C and C++ to do our GPU computing. So it's an extension. CUDA C is an extension of C. If you know C, if you know pointers, dynamic memory, then you will have a really easy time, I hope, learning CUDA C. There's also C++ features. There's even an analog of the standard template library. How many? Some of you have heard of STL, right? Yeah? So I'm going to get to that in a later lecture. It's called Thrust. It's very powerful, very nice. So if you know C++, even better. And we have CUDA-enabled servers at Iowa State. Impact 1, there's Impact 1, which works. Impact 2, last time I gave similar, I think on the introductory talk, I said that Impact 2 worked, but the GPU wasn't hooked up. Now the GPU is hooked up. And in fact, it's really the most optimal choice out of these 4 right now, because Impact 2 is the only one with CUDA version 5. The others have CUDA version 4 and below. This summer, I wrote a program. I wrote an Markov chain Monte Carlo in CUDA C, and I made the mistake of coding it only on Impact 2 with CUDA 5. It's apparently not backward compatible. The way I did it wasn't backward compatible. My program doesn't work on versions of CUDA that are less than 5, but I mean, you would, for now, I would try to write programs mainly in CUDA 5 that may be, backward compatible with earlier versions of CUDA. That would probably be the best strategy. But given the choice between programming something that only works in CUDA 4 and something that only works in CUDA 5, obviously you'd want to program something that only works in CUDA 5, which is Impact 2. Yeah, Jared.
Is the difference in the versions just the software, or is it also the hardware?
So for those of you online, the question was, is the difference between CUDA versions just in the software, or is it in the hardware as well? I think certainly the software is different. I haven't looked into this myself, but I would expect the drivers to have changed a little bit, because people are constantly coming up with new graphics cards. So there's a whole, in the CUDA API, there's a driver. There's this whole section on drivers, and then there's a section on user, more direct user interface stuff, and both I think are changing. That's my guess, but it's purely a guess. I'm not exactly sure, but it's definitely something to be aware of if you're to find out. Yeah, thanks for bringing that to my attention. I should go look that up. All right, let's get started with beginning CUDA C. I have some general things to say along the way as I describe 6 examples. So this is a beginner C program. You include your standard I/O library, allows you to print stuff out. You have your int main function. How many of you are comfortable in C, by the way? I should ask that first. All of you. Great. Sort of?
I used to use it for teaching.
Oh, okay.
I'm aging.
Okay. Well, you'll pick it right up then. If you've used it before, you'll pick it up. Needless to say, this is a beginner regular C program. You just print hello world to the console, return 0 inside your int main function. The smallest CUDA C program that I can write that's non-trivially CUDA C is the following. You would have this function that I'm calling my kernel. I have this, and its return type is void. And I have this prefix global in front of it, which I'm going to go over. And then I call that function inside int main. And the difference is, when I call this function, I have this weird triple bracket notation. And I'm going to go over that in a second. But this triple bracket notation is one difference between what you see in C and what you see in CUDA C. And so is this global prefix here. Let's take a closer look at this. This time, I have numbers 2 and 4 here. And you may get different results depending on what you put here. Let's go over what these things mean. The double underscore global double underscore says that this function is a kernel. And that'll be executed on the GPU one or more in or by one or more simultaneous threads. So this is a kernel. So when I call this kernel, the instruction set is going to be sent to the GPU, and then whatever inside the body of this function is going to be executed simultaneously by each separate thread. Make sense? So this is how I put that parallelism into code. Now I haven't actually done anything yet because the body of this function is empty, but we'll get to some non-trivial examples pretty soon. Some rules. If I want something to be a kernel, obviously, like I said, I got to put this global prefix in front of it. You also got to return void. So you can't have type int here for a kernel. If you want any return values from the kernel, which most of the time you will, I hope, sometimes, you're going to have to pass things by reference. And the pointers must point to things on the GPU. And then using those pointers, you'll write things back onto CPU memory. And I'll go over how that works a little bit later. So I went over this global thing. Now this weird, ugly triple bracket notation specifies the number of blocks. So in this case, the first number is the number of blocks. So I'm calling this with 2 blocks. And the second number is the number of threads per block. That's 4 right over here. That's the number of threads per block, not the number of blocks. So I'm calling my kernel on with 2 blocks and 4 threads per block, which means I'm calling this kernel with 8 threads total. So far, so good? Yeah? Moving on. So this global thing right here is called a prefix. There are a bunch of prefixes in CUDA C that I'm just going to briefly talk about. So there's the host prefix, and which you can put, by the way, you can put any prefixes or what go in front of this function, any function. And I think that's standard in C as well. If you put host in front of a function, it runs once per call on the CPU. So when you call it, doesn't run in separate threads. It just runs like a regular C function. Host functions are only callable from the CPU, so either from int main or any other host function. And all functions without explicit prefixes are host functions. So you get the normal functionality of C. You don't have to go through and specify what every function is unless you're really pedantic. Global prefix, used to specify a kernel. And global functions run multiple times per call on the GPU. So whenever you call global, you have to call, number of blocks and number of threads per block. And it runs this number times this number many times. And it can only be called from the CPU, but it specifies an instruction set that's actually executed on the GPU. And I say that because there are also things called device functions. You don't want to just have kernels because you may want to break up instruction sets in the GPU into multiple functions. And device functions allow you to do that. They run once per call, and they can only be called from kernels or other device functions. And so you have functions that run on the host, and you have global functions which send things to the GPU. And then you have device functions to break up each thread's instruction set. So you get no parallelism out of device functions. They're called from kernels or other device functions, and they run once per call. Does it sort of make sense? I know I haven't done examples of this yet, and I won't really for a while. But here's a skeleton to sort of say what I mean by that. So I have two device functions, a global. It says, please run this 10 times. And here's my int main. So when I go through it, I call this int main. This int main runs on the CPU. And then I call, please run this 10 times, out from the CPU, runs with 2 blocks, 5 threads per block. And so whatever's in the body of this function now runs on the GPU in 10 separate simultaneous threads. Each of those threads separately calls dev1 and then dev2 and calls them once. I can't spawn an additional set of threads or blocks in either of these because they're device functions. So each of these gets run once per thread. Make sense? That's most of the difference between C and CUDA C. You've already seen most of it. It's actually applying it that's the tricky part. And even trickier is debugging everything because it's really hard to write. Zeb's nodding, he knows. It's hard to write things back to the CPU and be able to parse that output in a way that allows you to find the problem. It's also hard to set up sophisticated debugging tools for functions that are supposed to manage memory on the GPU. Zeb's done that, and I borrowed his code, and I'm very grateful. So that's what kernels and device functions and stuff like that are, extra notation that I'm going to use in my examples. But there's also this business of memory mapping to the GPU, allocating memory to the GPU. So that's a bit tricky, and that's cumbersome. You have to, when you're writing CUDA C programs for the first time, you sort of have to take a, you have to take a template that already does that to really be able to do that. It's one of the hardest parts of actually starting to programming in CUDA C that at least I've come across. Once you get over this barrier, though, and actually figure out how to map memory tune from the GPU and actually do it right, then you're going to feel a lot more fluent and fluid in computing. But this is the general workflow for a program that does all that memory stuff. So we have some kernel here with some arguments and some work inside. A couple libraries at the top. There's CUDA.h and CUDA runtime.h. Those are the user API and the driver API. There are 2 CUDA APIs, and apparently including both of these libraries covers both. I don't know exactly how that works, though. But anyway, so we have a kernel, and here's what happens inside the main function. So most of this is in comments because this is just a schematic of what the steps that you're generally going to take in a CUDA C program. You're going to declare all your variables. You're going to allocate any dynamic memory in the host using malloc or calloc, tools that you should already be familiar with. How many of you do not know how to use pointers or dynamic memory or malloc in C? Good. All right. Everybody knows. All right. So we dynamically allocate memory on the CPU, but you got to also dynamically allocate memory on the GPU because you're going to actually be working with stuff on the GPU. We want the same storage there. Anything that you're going to write to the GPU or work on with the GPU in the GPU, if you're passing by reference, you're going to need to allocate some memory. So you do that here. Then you fill up your host variables. You can initialize them if you haven't done so already when you declared them. You got to copy that memory to the GPU or to the device. You got to copy this memory to actually be able to work on it. Because when you pass pointers into kernels, those pointers better point to things on the GPU. If you pass pointers to things that point to memory on the CPU, then it's going to have some error. So those pointers have got to point to things on the GPU. So those pointers that you initialized when you declared your variables have got to actually point to memory that you've actually written to the GPU. That's what this step is for. So it's a lot of overhead. It's a lot of work to even set up a CUDA C program. But it's worth it because you actually get to execute the kernel next. And that should run really, really fast if you do it right. So you're finally ready to execute the kernel. You do it. Now you're done. Unless you want to execute more kernels. Now what you do is you got to get the results back. So you've done some calculations, and those calculations exist in memory on the GPU. You got to write those back to the CPU. So what you do, that's the next thing you do. And then once you have stuff on the CPU, you're basically done, and you do whatever you need to do in ordinary C in order to finish up. Remember to free your memory though. Free the memory on the CPU with the function free, and then you free the dynamically allocated memory on the device with CUDA free. And memory leaks are hard to debug in general. And you guys know about free in the context of regular C. If you're having trouble debugging memory leaks, C programmers a lot of time, I started using Valgrind. How many of you know about Valgrind? Yeah? A couple of you? Valgrind is a great tool. I highly recommend that you start using it for regular C programming. It diagnoses memory leaks, diagnoses them very well, except it may give you some false positive errors for GPU computing. Don't worry about those, but regular C programming is great. And there's an equivalent very good program for GPU computing called CUDA memcheck. And so you would want to check CUDA C programs using both CUDA memcheck and Valgrind to help diagnose memory leaks. So there's this program, my first real program. It's called simple.cu, and it's online. I'll tell you where that is later. So all it does is it takes a variable that has the value 0, and it uses a kernel to change that value stored to 2. And it writes the result back and then prints it out. Very simple. All I'm doing is flipping a switch right here. So I have this global kernel, yeah, that takes in a pointer to an int, and that pointer, remember, points to something on the GPU. And all it does is it sets the value pointed to equal to 2. That's all it does. And here's what happens in int main. So I have this variable a, which I initialize to 0, and then this pointer to an int, a sub d. Now, the subscript d is often used to denote variables that are pointing to things on the device. So I could have a sub h and a sub d for a host and a device, respectively. That's a convention that's often used. I often use it in my CUDA C code. Well, those are your variables, and you want to make sure, whether you do that or not, you want to have a good system to keep track of what's pointing to things on the CPU, what's pointing to things on the GPU. It's very important to stay organized like that, because in code there's really no other way to know except for your own methods of organizing and keeping track of things. So remember, the next step is allocating memory. So since this a is, I just set it to 0, it's a regular int, I don't need to allocate memory for it. But I do need to allocate memory for a sub d on the GPU. And then there's this function called CUDA malloc that does that. So I say CUDA malloc, and it actually takes a pointer to this pointer that I want to fill. Actually, so if I want a pointer to an int to point to an int on the GPU, then I'm going to pass CUDA malloc a pointer to that pointer to an int, and I'm going to tell it the size that I want. So if a sub d were an array of length n, I would pass in my second argument as n times size of int. So you can work with multi-dimensional arrays, one-dimensional arrays very easily. Multi-dimensional arrays are very difficult. I'm just going to say that right off the bat here. I would avoid as much as possible using multi-dimensional arrays, and I'll go over in later examples and later talks how to do that. So that's CUDA malloc. In general, when you call CUDA malloc, you're going to want to wrap it inside some error checking function. I don't show that here because I want to keep things simple. But CUDA malloc has a return type for diagnosing errors. And you want to keep track of these CUDA malloc errors because they're very elusive and they're very hardware dependent. So I would write a macro. In a later, more advanced example, I'll show you a macro that you can write to check errors with CUDA malloc. You just wrap it around here. I'm not going to go over that now, but in your own CUDA C programs, please do that. Same thing for CUDA memcopy. Wrap an error checking function around that. And CUDA memcopy copies some memory on the CPU to memory on the GPU. That's the next step in this program. So the first argument is the thing that's copied to. The second argument is where the information is coming from. And they both have to be pointers. So I'm copying memory pointed to by ampersand a. That's just the pointer to a into a place pointed to by a sub d. My third argument is a size, so I'm going to copy one int of things, and I'm going to say where I'm copying to, where I'm copying from. So this last argument is, I think it's a macro defining one of the headers. It's probably just some number, CUDA memcopy host to device. And that just says that, well, this points to something on the GPU, this points to something on the CPU. This is always your destination, this is always your source. But whether this is the GPU or this is the CPU or the other way around, you got to specify here. And that's CUDA memcopy. Again, use error checking on that. Very important. When I was writing my MCMC that I told you about before this summer, I would have been in a real bind if I had not had some error checking in CUDA memcopy, because how I was implementing it was extremely memory inefficient at first, and I ran the program. When I scaled down the data, I had no problems. So I thought, well, I shouldn't run into any problems when I scale up the data to several thousand rows by 8 columns, right? But I had problems, and I would have been just baffled. but my error checking function told me that I was running out of memory on the GPU. I had just maxed out all the main memory on the GPU. I would not have known that in a million years if I hadn't put some error checking around CUDA memcopy. So again, very, very important. But I don't do it here because I'm being a hypocrite for now. I want to keep things simple. Moving on. So now all this setup, and I finally get to call my kernel. I call it with 100 blocks and 100 threads per block. Very, very redundant, but I'm okay since every thread does the same thing. On the same data. Usually threads are going to be different. Might behave slightly differently. I'm going to go over how that works, but in this case we're okay. I call 100 threads, 100 blocks to 100 threads per block on a sub d. A sub d is a pointer to an int on the device. Passing this pointer. This pointer gets set to 2. Previously it stored the value 0 because I copied it from A, and A stored the value 0. So now it turns from 0 to 2. Now I want to write that back to the host. So I call CUDA memcopy again, except this ampersand A is my destination because I want to copy back to the CPU. A sub d is my source, and I'm still copying one int. But now I'm saying CUDA memcopy device to host because, well, I'm copying from the device to host. And then I'm basically done. I print out my result, and if I use CUDA free, very important, CUDA free, to free my dynamic memory on the device. Very important also to put some error checking around this last one, though, this CUDA free, because you may run into some problems there. Usually not catastrophic ones, because usually all the frees are at the end of your program. Compilation. So I would run this command, nvcc. I'd put my source, -o, my binary, just like using GCC. And then I run it just like any other binary that you compile in C with a // and it outputs a equals 2, which is exactly what I want. You all good?
So did you write over that A like 10,000 times?
Yes, I overwrote this a sub d, 10,000 times, which I'm writing to the same data here. That's not what you should be doing, but for the sake of a really, really simple example, I violated the single instruction multiple data paradigm, and that's just really, it's redundant and unnecessary and dangerous, and I shouldn't have done that. Yeah.
Even in 100 different blocks?
Yes, 100 different blocks. Yep.
Same memory?
Yes, the same memory, because I haven't gone over memory yet. I'm going to go over it next week. But this a sub d is on what's called global memory on the device. CUDA memcopy puts things into global memory, and anything in global memory gets shared by all the threads and all the blocks. Yeah. Things that you defined inside the kernel, though, are specific to each thread, usually, except if you make them shared memory, which I'm going to go over next week. Yeah?
When we have multiple GPU cards, then how to put some parameter to share some?
That's a good question. So for those of you online, the question is, what do you do if you want to parallelize this instruction set over multiple GPUs? I have not actually done that. And I don't know what you would do to specify what graphics card you're going to use for what instruction set, but you would need to write memory individually to each graphics card. So you would be executing different kernels on different cards. So that's really what you have to work with, because those graphics cards only share memory through the CPU. So you would have to read and write back to the CPU to micromanage that.
Individual.
Yes, individually. Another question?
Basically, what he's asking is to do MPI with the GPUs.
To do MPI?
Yeah, that's what he wants.
Okay.
So you have to use some MPI programming on top of the usual CUDA.
Okay.
That's all.
Thank you.
And there are, we use that. There are Python libraries like PyPark, which allow you to do that without having to go through all the hassle of MPI.
Okay, thank you. So I didn't know about MPI. So for those of you online, on the answer to the previous question, a better answer to the previous question is that you can use MPI to micromanage multiple graphics cards for you and make things easier. I don't know anything about MPI, so this is new to me actually.
MPI is hard to program, but you can use PyPark,
Okay.
Python library, which, then it's very easy. And we've done that.
Okay. Wonderful. Another one, yeah.
So my question is that so on the fourth line in the main function, so the pointer to pointer, so you use the void pointer pointer, but the type or the original type was actually int pointer, right? So that means in CUDA there's we always use void pointer to pointer. We never keep the original type, right?
I'm not sure I understand your question. Are you confused about why we have a void star star here?
Yeah, why is not int star star?
I'm not sure. I think that's because definitely because of something internal that happens in CUDA malloc. Generally, I found in programming when I need to. I mean, my best answer is that it's something internal in CUDA malloc specifically. Everywhere else where you write GPU code, CUDA C code, you would write it like you think you would, with just that pointer, not a pointer to a pointer usually. From my personal experience, when I'm writing programs and I pass a pointer to a function, and I want to allocate memory for that pointer, I can't pass that pointer by value. I've got to pass it by reference, because now when I call CUDA malloc on a pointer, it's modifying that pointer as if it were an ordinary variable, right? So when you call CUDA malloc, or when you call malloc, you're not modifying the memory you're not only modifying what that pointer is pointing to, you're modifying the pointer itself. Because the address in that pointer is being changed to point to some memory location that is available. Does that make sense?
So another question is, do you also have to call the say free function on the variable AD? Yeah, you use the CUDA free. Do you
Yes.
also have to use the say free function?
On A sub D?
Yeah.
Nope, CUDA free will do it, because A sub D points to memory on the GPU, but not to memory on the CPU. So CUDA free will free all the memory associated with A sub D, because A sub D points to the GPU. Ordinarily, you would have to call free on A. So I have a GPU analog of A, on which I call CUDA free, and I have a CPU analog on here, a CPU copy. But in this case, I don't need to call free on that because I didn't dynamically allocate memory to it in the first place. Does that make sense?
Okay, thanks.
So although there's one memory location on the host,
Right.
there could be multiple on the device, right?
Multiple memory locations?
Yeah.
Yep.
That's why you have to free all. I mean, for all
Right.
of these calculations, you should be essentially using tons of, 100 by 100,
Yes.
10,000 or whatever.
Right.
Is, right?
Right. You're going to have a lot more memory locations, a lot more variables, and you're going to need to free them all. Yep. Good. Anything else? All right. I want to get through at least one more example today. Back to compilation. So NVCC, I just told you how to compile this program. NVCC stands for the NVIDIA CUDA compiler, CUDA C compiler. And It comes with every installation of CUDA. It's a lot like GCC or G++, but it has some idiosyncrasies that I'll get to you when they come up in future examples. And just a convention, I have this .cu here. You're used to seeing .c or .cpp. You can use those extensions if you want still. .cu is also a common extension for CUDA C programs. And this code's available on my website under this. Actually, I need to update this URL because I changed this CUDA C directory to something else. No? Yeah, I'm going to need to change that URL. But it's online. There's a page for this on my website for this talk specifically, and you can download all the code there. And you can find other examples similarly. So I haven't used, in order to move on to more interesting examples, we need to talk about built-in CUDA C variables. You want to have each thread execute instruction sets on different places in the data, right? So in order to do that, you need to know something about this stuff. So first of all, max threads per block is exactly what it sounds like. It's the maximum number of threads you can have in a block. That's exactly 1024 on Impact 1, for example, and it's that same on, in fact, the rest of the Impact servers. Now, there's typically 1024, and by this I mean number of threads in the x dimension. There are y dimensions and z dimension, and there are two other dimensions of threads that you can allocate, which I haven't gone over how to do yet. So there's also 1024 in the y direction on our servers and 64 in the z direction. You can allocate far more blocks than threads per block. So it's for blocks, you can allocate about 65,000 blocks in each dimension. And we have an order of magnitude less for threads per block. So just keep that in mind for your code. So for CUDA C variables that actually allow you to tell threads to go to different places in the data, you need the following. So let's say we have b blocks and t threads per block. So there's block idx.x, which is the ID of the current block in the x direction. And it's an integer from 0 to b minus 1. We have thread idx.x, which is the analog for the thread per block. So it's the ID of the thread within the current block. It's not, and it's an integer from 0 to t minus 1. Remember, this is the index of the thread within its block only. So there are b threads with thread index 0, for example. Does that make sense? All right. So there's grid dim, which gives you the number of blocks in the x direction, and there's block dim, which gives you the number of threads per block in the x direction. There's also .y and .z of all 4 of these, like I say. So let's use this information to actually compute the sum of two vectors. So I have this global function, this kernel, I call it add, takes a vector a, that's an int pointer b, and an int pointer c. Instead of a for loop, I have the following. I give bid the index of the block, so it's block idx.x. And I say if bid is less than n, if this index is less than capital N, where capital N is the number of elements that I should have in my vector, n is a macro for the length of the vector at the very top. Then I'm going to let C be the sum of A and B for that component indexed BID. So block BID sums the BIDth element of A with the BIDth element of B. And it stores it in the BIDth element of C. And all of the elements of C get summed up simultaneously because these blocks execute simultaneously. So that's the kernel. Now for the rest of the code. So I have an integer I, and I have vectors, arrays rather, A, B, and C of length n on the host. Dev A, dev B, and dev C. That's another convention for writing things on the device. Those are all int pointers on the device. Vectors A, B, and C there. I use CUDA malloc to fill up A, B, and C for each one with blocks of memory the size of n ints. I initialize I fill the vectors on the host, and then I copy them to the device. So I copy everything in A to dev A, and the same thing for B. I call this kernel with capital N threads, capital N blocks, because remember each block has one component to sum up those vectors on, and one thread per block. And I'm going to call it on dev A, dev B, and dev C. Because remember, these are all pointers that should be on the device, right? Or point to the device. The addresses themselves are stored in objects on the CPU, but they point to things on the GPU. That's an important distinction. So there are pointers that are fully stored on the GPU. The pointers that I'm working with are stored on the CPU, but point to things on the GPU. And that's what I'm working with right now. And I call add, which does this parallel addition. I copy the results. The results stored in dev C, but I can't print that out to the screen yet because it's on the CPU. On the GPU. I can't print things out to the screen when they're on the GPU fully. So I copy that to C using CUDA memcopy. And then I print out C. And then I call CUDA free on each of dev A, dev B, and dev C because those pointed to things on the device. If you try to call CUDA free on a pointer that you created inside some kernel, let's say on the device, then you wouldn't be able to call CUDA free on it. CUDA free is called on pointers that exist on the CPU and point to things on the GPU. I don't need to call free anywhere because I already freed, I never allocated anything in the first place on the CPU. All right, and I compile it just like before using NVCC, and I execute it, and here's my output, just to verify that it works. And you can log on to Impact 1 and run it yourself. I am not going to have time to, I'm going to try because this is important. So I might pick up where I left off last time, next time. So there's this thing called the pairwise sum, and it illustrates why we need blocks, because we need to synchronize threads sometimes. So let's take the pairwise sum of this vector as an example. So I went over it last time. So I spawn one block with n over 2 threads, where n is the length of this vector. So I have 4 threads because there are 8 things here to sum up. And what I do is the first thread takes first the 0th and the 3rd element. So element here and the element 4 places down. Second one takes the second thread, thread 1, takes its element and 4 places down, sums that one up. Third one does the same thing, takes an element and the element 4 places down, sums it up, and computes all those paired sums. I need to synchronize those threads because before I move on, you know we're going to need to sum up these 4 things, but you need to actually have these 4 things computed before you take some more sums. I mean, you can't sum up -1 and the thing here if the thing here doesn't even exist yet. So we got to do things in chronological order, so we need to synchronize threads. And now in the second iteration, this is very important to understand the code. So you're going to take, in the second iteration, you're going to take this thread, and you take an element and you sum it up with a thing that's 2 places down. Next thread, you take an element and the sum with something that's 2 places down. You sum that up. So the offset here just got halved. I just divided it by 2 for this step. Synchronize threads again, and I sum the last 2 elements. So really quickly in pseudocode, well, I'll skip the pseudocode. You can read up on it. This is formally what the pairwise sum is. Let's go to the actual code, where I have this global psum here. So I let t be the thread index, and let n be the number of threads. So t is the thread, and n is the number of threads. And little n should be half the length of my initial vector. And I control that because when I call the global, I can give it the number of threads that I want. And the number of threads should be half the length of the vector. And I take care of that inside int main. And then this while loop does the thing that I just described. So while n greater than 0, n is the offset. So my first sum, I had an offset of 4, right? I sum each element with the element 4 places down. Imagine I have a vector of length 8. N is going to be 4. So if t is less than n, if t is less than 4, I use these 4 threads to do the following. So I add up the vector at t with the vector at place t plus the offset n each time. And since t is the thread index, all these sums get computed in parallel. And then I synchronize those threads to make sure every v sub t for t less than n has all of my pairwise sums so far. Make sense? And after I synchronize threads, remember, I need to divide that offset by 2. Remember, because I had offset 4 in the first stage. Then after I synchronized threads, I had offsets of 2 for the second stage. Remember those diagrams? That's why I divide by 2 here. And then I sum up those pairwise sums so far in another iteration of this while loop. N decreases each time because I integer divide by 2. And when n equals 0, I'm done. And my my return value of the pairwise sum should be the first element of this vector by the time I'm done. And then the rest of this code is pretty simple. It just involves allocating memory and writing things out. Remember, the important thing, though, when I call psum, remember I need one block and half the number of threads that there are elements in the vector. That's what this says, one block and over 2 threads per block. And then the rest is just allocating memory and stuff, which I went over already. You can run it to check codes online. Now, remember to respect the SIMD paradigm, single instruction, multiple data. So we want each thread to write to different memory spaces. You don't want 2 different threads writing to the same variable, which means if I pass something in global memory, you don't want each thread writing to that same thing on global memory. I know I violated that rule in the very first example. In that case, in that specific case, it didn't matter because it was so simple. In general, you want to be careful. So here's an example where I have this kernel. I pass in by reference an integer. That integer is on, and that int is on the GPU, and I give that int the total thread index. So blockdim.x times blockidx.x plus threadidx.x. That's an index from 0 to the total number of threads, and each thread has a unique one of those. So this thing is going to be different for every thread. And I call this thing with 4 blocks and 5 threads per block. And then I write it back and return it. What value is this thing going to have at the very end? Oh, it would be freed, but before I free it, I write it back. I write the value back to the CPU side and print it out. So by the time I print it out, what do you think it'll be? Not sure. Correct. Correct, because the value that I print out is going to be the value of the last thread that worked on it. So you have multiple threads trying to compete for this memory location, right? And only the last thread to go is going to have its final value stored. Because when the first thread tries to write to it, right, and then leaves, and the second thread overwrites it and then leaves, and the third thread to execute overwrites it and then leaves. So you don't know what value you're going to end up with. If all those threads are writing the same value, like in my previous example, fine. But this time, I'm writing different values. When I compiled it and ran it, A was actually 14. So A could have been, depending on the hardware, depending on a lot of random things over which you have no control and can't predict at all, and aren't even random with any distribution that you care about. A could be any number from 0 to 19, 20 possible values, and it's unpredictable, and you really don't know why. And that's sort of the thing called a race condition. You want to avoid race conditions. You avoid race conditions by having threads write to different places in global memory. All right. I apologize for being 5 minutes over, but we have a couple of questions here actually. Yeah. Okay. Yeah, I'll take your questions afterwards. Just note this is what we covered. I barely got through all of it. Sorry for the extra 5 minutes. We have these two texts, which you can see when you go and look at the slides online if you want. And the code is online. Code is at will-landau.com/GPU. And everything is linked to that website. Thank you for your time. I will see you next time.